Now let's take a look at the jump diffusion model. The jump diffusion model actually has two random movements here. One random movement is related to this dz, which is the Wiener process or the Brownian motion, and the other one's related to this Poisson process. Now, here the change is actually continuous, but for the Poisson jump, it is actually a discrete. Now, in the Poisson jump here, there is actually an expected change. So we have to correct that because you have it here, which not just random, this also has a expected change here. So you have to correct that expected change by reducing the drift by lambda times k. So let's take a look at what some of the parameters here. Now in the change here, this Poisson jump follows the Poisson distribution here, and this distribution determines a number. So when you draw out of this distribution, you will draw how many numbers of jumps in a period of time, and with an average lambda here. Lambda is really the average number of jumps per year. Okay, so essentially the Poisson distribution gives you, if we have an average jump per year, say 30, then let's say you want to see what is the jump I'm gonna get for 1 month. You can draw out of this, and then you will get a number. Then the number it's a random number. That random number will tell you in this particular realization how many jumps you already have. So and if an average is 30 in a year, then you may get 1 jump or get 3 jumps. So as the realized number of jumps you have for that particular period of time. Now, you only know how many jumps you have, but you don't know the size of the jump, right? So you also need a jump size. The jump size you can actually draw out of a different distribution that will give you, so you will, from Poisson, you will know how many jumps it will occur in this 1 month. And then for each of the jump that has occurred, you can draw out of a distribution that give you a realized actual jump size. And K is really if K is the average jump size, so lambda times K is the expected change, right? So you have to reduce this expected change from here, from the drift, because that expected change is actually here, implied here, to ensure that you do have a risk neutral process where the expected change must be equal to this, meaning that expected change is equal to R minus Q. And you've added lambda K here, you should subtract that lambda K here. Now, Merton has shown that if we have a jump diffusion process, you would actually have a quasi-closed form solution. What that means is that you will have an expression, but this expression is an infinite sum. So it's not really a true closed form solution, because you have to use some numerical routines to calculate this infinite sum. But now, nevertheless, it's a simple enough procedure So you can calculate the options, simple options, using a relatively simple formula that involves a numerical sum. Now, once you have done that, you can obviously use it to calculate well, you know the option price based on that quasi-closed form solution. So as we mentioned earlier, that you're not going to use it to calculate simple options. So the price of simple options you observe in the market will then be used along with this quasi closed form solution to calculate the implied parameters that we have on lambda, on k, and those ones. And then once you have that, you can then use those parameters as given, then to calculate complex options using numerical routines. Now, for the jump diffusion process, this model gives heavier left tail and heavier right tail, which means that this is actually very suitable for using to be utilized for currency options, because they as we have seen that for currency options there are volatility smile rather than volatility skewness. So let's take a look at how an option, a more complex option, can be calculated if we were to have the required parameters backed out from that quasi closed form solutions that we have. Now to implement a Monte Carlo simulation using the jump diffusion process, you will first obviously to create a change based on the diffusion process, right? Which is the usual way that we have described before. But on top of that, you have to do two things. One is to determine the actual jump process, and then you have to subtract an average, obviously, from the mean, from the expected change there. So to do the Poisson jump, you will then once you have the lambda and the k, what you will do is you will generate a uniform, a random number from the uniform distribution between 0 and 1. And then from the inverse cumulative Poisson distribution, that whatever number you draw out of this uniform distribution would determine how many jumps you have occurred for one time step. And then you can draw out of a distribution, give you the actual jump size. And then for that, you'll calculate what is the actual jump changes that occurred in one time step. And then, then attach that to the change that you have produced from the normal diffusion process, and adjusting for the expected change, you'll then get the actual change that you will be simulating. So you do that for one time step, and you could do that for multiple time step. So you just do exactly the same thing for each of the time step, then you generate your path. And then after that, your calculation option will actually be exactly the same as you would have done before for just a pure diffusion process.